This podcast is brought to you by LMU Munich.
Okay, so our keynote will be done by Andreas. It's pretty cool. Thank you very much for coming this morning. Before we start, can we please cheer our volunteers to do another hard day today, yeah? All right, guys, enjoy and let's have a great conference.
Ja, danke. Yeah, I just start. So, hello everybody. I really enjoy this conference. It's really nice and cool to be here at the PyCon after missing the conference last year very sadly. So, and it's really a pleasure that I can give actually two talks. I've had one yesterday and one today. It's really great. And what I'm talking about today is it's not about warp speed, actually. But I gave this title and then I thought about the content. So, but it's about making Python faster on different kinds of systems. Maybe related to high performance computing, distributed computing and quantum computing. Just a few words for me. I'm working as a daily paid job as a scientist at the German Aerospace Center, Deutsches Zentrum für Luft- und Raumfahrt in Köln and Berlin. I'm leading a department for intelligent and distributed systems. I've also co-founded a company, Medando, where we are developing mobile apps for medical applications. And my major role there, I'm the major patient of this company. I'm testing all the apps. With my illnesses, I give the requirements. And I'm also attending in community events like Quantified Self Meetup. I'm going to PyCologne every time when I'm in Cologne. I'm organizing a conference series, PyHPC. And I was supposed to organize PyData Cologne this year. It should happen at the end of November in Cologne. But then we had a fire in our casino, in our conference center at DLR. And we have to postpone the conference. So the conference center is not usable for almost 1 year. And we will see what happens if we can get another location. But there will be someday next year a PyData Cologne conference. That's sure. We do not have a location yet. So the German Bundeswehr, the Luftwaffe offered their location, but that would be difficult with like people from outside of Germany. Okay, so the topic for today is Python at warp speed. And as I said, I'm talking about not really warp speed as a technical issue or as a technical concept, how to realize that. Some people think that we are doing something like that at DLR, at the German Aerospace Center. That's true, yeah, but that's more the technical engineering side. I'm at the software department and we are talking about software, and in the sense of speed and performance, there are three aspects where I want to talk about and where I think I could share the current state in this field. This is one thing is high performance computing. Next thing is distributed computing, and the third thing is quantum computing. And these two fields, or these three fields, they have different kinds of applications. If you see the algorithmic view, if you have an algorithm with an input X and an output Y, then high performance computing is mainly for computing the Y at the end. Huge vector matrix multiplications and all this stuff, solving linear equations and so on, very huge data sets. Distributed computing nowadays is often used for learning, for machine learning and data science. It means learning the algorithm with the result and the input set, a training set as inputs, and algorithms learn software learns the algorithms actually. And the third thing is quantum computing. And quantum computing today, the systems that are available, are only good in optimization, solving optimization problems. They cannot do anything else. So I'm going to present a few details on each of these topics now. So, yeah, I start with high-performance computing. This is a field, it deals with like raw computing power for large applications. Not only science applications, but is really much driven by large science applications, large use simulations, like things that we are doing at DLR, simulating airplanes in all kinds, or simulating in the field of earth science, or simulating in the field of theoretical physics and astronomy and astrophysics. So typical fields where HPC is very important and widely used. And typically here is we have huge performance, or we try to have huge performance on multi-core computing systems, and huge performance on a single core, on multi-core, and very huge machines, actually. That's very typical for today's high-performance computing. And machines is like, we're talking about this kind of stuff. This is from the top 500 list of supercomputers, which is published every, 2 times a year. So at the ISC Supercomputing Conference in Frankfurt in Germany in June, and the next edition will be published in 2 weeks at the Supercomputing Conference in Salt Lake City. So the current #1 system is from China, Sunway Taihu Light, 10 million cores on the system, 39 petaflops. This is just very much. Even the iPhone 7 cannot reach this number. And the important thing here for the high-performance computing guys, the interesting thing here is not the number, but it's the fact that the processors come from China. While in all other systems, like the second largest, Tianhe 2, also from China, 3 million cores, I think the processors came from Intel, AMD, or NVIDIA. And also the number third, in the top 500 list is the Titan system. I think it's an Oak Ridge National Lab in USA. 560,000 cores, much less than the #1 system with 10 million cores. But it's still fast enough to be in the list. And they also use like standard processors from the US. So, but how to program these kind of machines? I mean, they're looking very good, but is it true for the software too? So programming HPC systems is, I mean, there are a lot of technologies, and since this is a keynote talk, supposed to be a keynote talk, I'm not going into details in each of the topics I'm presenting now. So, but there are technologies like message passing interface, which I have to mention because my boss invented it. So it's very cool and nice technology, so I have to look in the camera. And there are also things like OpenMP and OpenACC or Global Airways Toolkit, CUDA, and OpenCL for graphic cards, and so on. And you can use this kind of software technologies. These define like the messaging between cores and the data exchange and so on. And the languages that are being used is, there's Fortran, and then some people use C, and a growing number of people are using Python. Yeah, and that's the interesting stuff. So Fortran is, I mean, this is a Fortran book from 1953 or 57, very old, but people are still using it. I hope that someday people will present such a book cover from a Python book from 1993, and we are still using it in 50 years or so. That's my really hope. Yeah, I mean, as I said, so we are using, at DLR, we are using Fortran codes a lot in many applications, and others are using C and C++, but how is the performance of these codes compared to Python, or the other way around? So one example from our own department is we made a comparison with a helicopter simulation code from DLR. It's a code developed beginning in 1994 in Fortran and parallelized with MPI. And there was a performance optimization in 2013. So it's a very highly optimized code in Fortran and a good reference to to compare with different kinds of Python applications. There are a lot of, I miss the references to papers. There are papers about this code and the comparison on the performance optimization, and so a lot of scientific work that my colleagues have written. And we made a performance comparison, and so the basic, one thing was that we have written a pure Python implementation of the core simulation routines. They look like that, like a lot of for loops which have to be performed. It's the core loop of the helicopter simulations. They have to, I mean, you see things in the bottom, number of blades, it's like things like the number of rotor blades and so on. And if you compare that to the different languages, we found these numbers. On a single core system, for example, we saw that a higher bar is better in this diagram. Fortran is still the best. Then comes an implementation which uses Python. Then pure NumPy implementation is a pure Python implementation is really slow compared to, not only compared to Fortran, but also compared to the other implementation technologies. It's kind of similar on multi-core system, 6 cores. Fortran is still the fastest. The gap to Python is not as large anymore, and there's another implementation technology, Global Airways, which is also a bit slower. And then we have another comparison on graphic cards, GPUs. There we compared Fortran to Number with certain extensions, Number Pro, and also Fortran is much faster than the current state-of-the-art Python technology for that. Similar numbers and similar comparisons are discovered by other research groups in the field for different kinds of applications. And we are here talking not about like theoretical benchmarks or like classical benchmarks. This is a real code which is in production use for designing helicopters or for simulating helicopters. And I think this is our most interesting use case. Yeah? We are not interested in a synthetic benchmark or something like that. So you can condense this information from the different fields in this diagram. I called it performance productivity space. I didn't reflect if this makes sense, but I find this title of this diagram nice. And you can see, like in the performance, Fortran and also a bit C++ is ahead of all the Python technologies, but Python is still better in like productivity or simplicity in programming. We also find this out with the guys, like with students who worked in our projects on implementing this stuff with Python. They have definitely more fun and are quicker if they're implementing stuff in Python than compared to extending or implementing stuff in the Fortran code. Yeah. And this is true for, this is the case for students who have no knowledge about Fortran and no knowledge about Python before. So, equal starting point. So, a kind of summary, Python is, I mean, the productivity of Python is great. You can write your codes quickly. I mean, everybody in this room should know that. It's usable for a wide range of applications. This is not only for HPC and so, of course, also for web applications, all the other stuff. But the performance still needs improvement. So I think we are finished improving the Python performance when we are at the same numbers as Fortran. That's the goal. I mean, that's what we are working on, actually. And well, Fortran has like 30 or 40 or 50 years advantage. I mean, it was invented in the 1950s and Python 1990 or something like that. So Fortran has a long history of very good compiler development and code optimization technologies. And we have to learn that for Python and implement this in real application, in real compiler technologies and other performance enhancing technologies. But it's very exciting to see these advancements currently by the community in open source projects and also by companies, because not every progress is made in open source software, unfortunately. So regarding the community, this is like a small advertisement slide for the workshop that I'm organizing. Python for HPC and Scientific Computing Workshop, PyHPC. We run this workshop since 2011, and there are people coming with technical papers about their performance results, comparison to other languages, especially things like hybrid programming, because in most cases, nobody uses today anymore like a pure Proton implementation or a pure Python implementation. Usually you do like hybrid programming, mixing at least two different languages and so on. Yeah, so the workshop, if you want to come, it's November 14th in Salt Lake City, located at the Supercomputing Conference as a workshop. And so the Supercomputing Conference is actually the place where all the supercomputing guys in the world are coming, like 10,000 people from all over the world, sharing ideas about new hardware, new software for HPC, and networking infrastructure, and all this stuff. Like I mean, at the conference, 10,000 people, like 5,000 are people from some companies who like to advertise their stuff on an exhibition floor. But it's really exciting. And so one of the companies that is coming there, and they're also giving a keynote at PyHPC, is Intel Software. That is one of the companies, beside others like Continuum Analytics or Microsoft or other companies, who are making like huge advancements for Python in general, and also for Python in the field of high performance and technical computing. For example, Intel is providing a profiling tool and a debugger, Intel vTune amplifier, where you can do like find performance leaks in your code. It's not open source; it's like a commercial software, but well, for some non-open source software, it's also really really cool and a really great software. I mean, another technology that what they are providing is an MPI library, which is based on Python and wrapped for using with Python. And it's also very good if you have an MPI, want to write your MPI program in pure Python code, and not just wrapping in a parallelized Fortran or C++ code just with Python. And the performance is also really great, and they are proving it all the time. So, just as a pointer and as an example. The next technology is distributed computing. Distributed computing this is one of my favorite pictures. It's also like I have it as a poster in the office, actually, from a paper from 1964. The central concept of distributed computing is that you're moving away from a central server or something into a really distributed computing infrastructure with peer-to-peer communication among the nodes. And distributed computing is today, in general, driven by things like data science with machine learning and predictive analytics and all this kind of stuff, where you have tabular data, time series, stream data, connected data, and so on. And usually, in many use cases, people are not using these huge HPC machines to tackle these kind of applications. I mean, some people or some companies do, but some are using just laptops. They start with laptops in this kind of field, and they scale up to use clusters or connected clusters and connected machines which are standing everywhere in the company or in the world, like real distributed computing. And each of these machines itself is not very powerful. It's not with 1 million cores or something. And we have typical, in this field kind of application, we have typical many-task computing. Many tasks where each task is probably not very huge. And we need technologies like distributed scheduling, and we have peer-to-peer data sharing, data exchange between that. So, and scaling up is very important in this field because, it's just an example for my what we are working on is, for example, we are working on space debris data. That's garbage in space from defunct satellites and exploding rockets and all this kind of stuff. And what we are doing at DLR and what other people are doing is gathering information about the space debris things in space with optical telescopes and with radar and with laser tracking. And then we do object correlation from this sensor data. I mean, calculating the trajectories and the ephemeroids. And then we also, what we really want to have at the end is a collision detection. We want to know in advance if one of these space debris objects would hit one of our satellites or the International Space Station or other things. And this is a production use case, and what's happening in the field of, so the computing infrastructures we're using with that is a typical really distributed computing infrastructure based on 0MQ and implemented in Python. And the computation routines for doing the object correlation are implemented in Fortran. Yeah. And we use like protocol buffers and so on for doing the serialization of data and this stuff. Yeah, well, but what we are doing now and in the future is scaling up this application when we are detecting like smaller objects. Like when we, like currently there are like 29,000 objects which are larger than 10 centimeter. It's easy to detect them, and 29,000 objects is not very much for a computing infrastructure. It's easy to do real-time operations on a daily basis for that. So the next step is objects larger than 1 centimeter, which could also damage a satellite very seriously. There are 750,000 objects, and from the sensor side we are also able to detect objects larger than 1 millimeter. And then we have 150 million objects already in space, which we can detect now. And we also want to do all the calculations on a daily basis in real time for this kind of data. And the next step is when we're talking to other sensors, for example, we want to place optical telescopes in space on satellites where we are much nearer to the objects and we can detect much smaller objects. Then we have much more of these space debris objects. Yeah, and so the computation for this kind of calculations it's actually a graph of computations. I mean, there's object correlations and collision detection, and as I mentioned, and a lot of more of these kind of computations. And it's like when new sensor data comes in, we also go to this graph and produce a lot of like data products, which then is stored in one or more databases and is used in the Space Operations Center for the missions which are going on. And so this is the typical concept in these distributed or in today's applications with very huge data sets with like tabular or time series data, where each of these data sets is very small. Yeah. And usually, in many applications, this is based on graphs. We have a graph of computations which have to be performed. It's a different scenario to the HPC case, where we have one single simulation code which is distributed over one single huge machine. Yeah. Here we have many, many tasks which are distributed over your computation networks. And the important concept is graphs. You have graph computing, like the computations are directed acyclic graphs, or DAGs in this case. And also just to mention a couple of examples, the same as in HPC, there's a lot of advancements by companies and in open source projects for supporting these kinds of computations. For example, Spark or PySpark. Well, Spark is, itself is implemented in Scala and Java, I think, but mainly in Scala. But there's a Python API, PySpark, and you can use Spark for distributing your computation task in the distributed network. It's obviously very easy to implement with Python. Then another thing is Dask from Anaconda or from Continuum Analytics. Actually, the same concept. You can specify your computation graph and distribute or schedule it to your hardware, and specify the graph as a dictionary, for example, and then map or put this graph on your real computation hardware. This is a typical concept. And as another thing is, which is widely used, which is well known for machine learning today, is TensorFlow from Google. It's a library which actually had machine learning algorithms, but basically it's a distributed computing infrastructure where you can also build, like, it's not easy to see on this beamer, on this projector, but you also build a graph of computations, and you can distribute this computations on different resources like GPU systems or regular CPU systems and clusters and so on. And there are a lot of technologies from other companies, from Microsoft, or workflow systems like Luigi from Spotify, and much, much more. And many of them really support Python today, and that's really cool to see. But that's today. So more like going on to tomorrow is the next topic, quantum computing. Quantum computing, first, why are we dealing at DLR with quantum computing is because quantum computing, or because we have problems which are basically optimization problems, like, for example, design optimizations for new airplanes. So my engineering colleagues are working on very different concepts for making an airplane more efficient during flight or during operation. And this is also true for space systems and other systems, like transportation systems on Earth. And one of the most important things is really optimization in this kind of design, and also with optimization with uncertainties, if you're not sure if your formulas are correct and so on. It's very important, but also optimization problems arise in many other kinds of applications, of course, in all kinds of machine learning, with pattern recognition, image recognition, and so on, or anomaly detection, for example, monitoring of running systems. That's really a huge use case for monitoring onboard hardware on satellites and so on. Yeah. And detecting anomalies is very, very essential, so you can way ahead, or maybe an important thing is to predict anomalies in the future, so they can build a plan to replace a satellite or something, which takes some time today. Another important thing is mission planning, flight planning, and regarding to resource allocation or energy consumption and so on. An application which one of my colleagues is tackling with a quantum computer right now is flight planning of the SOFIA telescope. This is a telescope which is placed in a Boeing airplane in the back. It's operated by NASA, and we work together with them using this telescope. It's currently flying somewhere. It's currently based in New Zealand, and it's flying around New Zealand. And the flight planning for this airplane is very awful. I mean, you have to consider the plans and the wishes of the scientists, and also consider the weather and the astronomical stuff, that you can see the objects that have to be observed and so on. It's very a hard topic to do that in real time on a current system. Yeah? And so the plan here is to do the mission planning for the SOFIA telescope with the quantum computer. Another thing is validation and verification of software, especially for embedded systems. And many of these problems are actually like discrete optimization problems. They also arise in packaging, partition and mapping problems, scheduling problems. So the first application that the NASA did with their quantum computer was scheduling tasks on a supercomputer as a good scheduling algorithm. If you have a huge supercomputer with many users, many tasks, then the optimization of the scheduling is a very hard problem. Or another thing is scheduling of the daily work plans of astronauts on the space station and so on. And the hope is that you can solve these problems today with classical computing, but it takes a lot of time. And sometimes you need results in nearly real time. So, for example, if you are scheduling the daily plan of an astronaut and something happens, an experiment is broken or something, you have to reschedule. And currently this takes too much time. And the hope is that with a quantum computer, you can solve this within seconds or so. So this is an interesting technology, and where the foundations of this is, in a classical computer, you all know probably that we are working with bits, 0 or 1. Does anybody not heard this? Oh, no. Also Thomas. Great. But in quantum computer, it's a bit different. We have quantum bits or qubits. 1 or 0 is very easy to understand. And a quantum bit is a bit more complicated, and it's a composition or superposition of complex states, status of a quantum system. And as you can see here, people like physicists write it with this kind of notations. This is a quantum state of a qubit, actually. You can represent this in a space, usually in such a Bloch sphere, where you can represent this kind of state. So this is the basic principle. We have a quantum state, and this is not 0 with the brackets. It's not a real 0 in the sense that there's nothing, but it's a 0 with a certain probability. It can be 0, it can be 1, or something in between. And also for the 1. It can be 1, but it can also be some other state. We are here in the field of probabilistic computing. And that makes things a bit different and a bit interesting compared to classical computing. So what the quantum computer, so the systems that are presented earlier in HPC, they are available a long time, like clusters and all the systems. But also you can go today and buy a quantum computer. The list price is like $50 million. It's okay. I mean, they give, if you would go there and want to buy a system, they give you a rabatt, or how it's called, and you pay at the end maybe 8 million or so, but it's still a lot of money for the system. From a company, D-Wave Systems in Canada, next to Vancouver. And currently they have a system with about 2,000 qubits, D-Wave 2X machine. The principle is adiabatic quantum computing, which I explain later. This is the machine. It's like the size from here, like to here. And you can go inside. I was visiting the company last year, and I went inside one of these machines. It was an operation. It was actually the machine which was sold to the NSA, and it was in the test run at the it was not delivered, obviously. It was as a test run at the company, and I was asking, can I go inside? And they opened just the door and put me inside the machine. So I was inside the machine of the NSA. I like this idea very much. I was not allowed. So one thing, it was like just any other machine. Yeah. The people from the company D-Wave didn't have a clue what NSA was doing, like as a test case on the machine, actually. I was not allowed to take a picture of the machine for the NSA. That's an interesting fact, because they had 10 machines in the hall in the company. All looks exactly the same. I could take photographs of all of them, just not of the NSA machine. It's weird. But, yeah. To have a deeper look into this machine, I mean, at the end there's a quantum processor somewhere deep into this machine. It's not really like silicon, but a similar material manufactured as a usual, typical chip manufacturing company somewhere in the US. And there are also these qubits implemented. So the machine inside, they have, of course, a huge cooling system because the machine and the processor runs at 50 millikelvin, yeah, or lower than 50 millikelvin. And the important engineering stuff and is cooling down the processor to this cool temperature. And this cooling down process takes months or so. So switching on a quantum computer or rebooting a quantum computer is not a good idea. It's not. NASA had also D-Wave has sold like 4 machines today, 3 machines actually. Oh, it's recorded, but anyway, they talk about 3 machines. One is aerospace company in the US, one is NASA together with Google. So actually it's located at NASA, but Google paid for it. But NASA said other way around, but it's a different topic. And the third one is in Los Alamos National Lab. And the fourth one is at NSA, but they're not talking about it. And it's not on the web page and so on. But NASA did reboot the system once. It took 3 months to reboot the system. It's really, you have different time scales here in quantum computing. Yeah? And also, so on the processor side, I show the processor in one of these little cells, which you might have seen on the processor picture. There's this little ring of some material, and there's a current running around. And you have a magnetic field, and with this magnetic field, you are like inducting this current and like programming the quantum computer. And making a computation, actually, also you have a different kind of time scale. If you are putting like a current on this, it takes like 1 second after that to cool down the system again. So the processor cycle is 1 second compared to like what we have in the laptop, gigahertz, megahertz, I don't know, a very different time scale. So, and also very different to current processors is like programming for this kind of stuff. For example, the qubits on the processor are arranged in a certain topology. On the D-Wave machine, you have groups of 8 qubits which are connected. And in quantum computing, in quantum theory, you have qubits and connections between them. And they are entangled and they influence each other. But on this real hardware, you cannot entangle one qubit with any other qubit. You can only connect in these cells, or some of these cells can connect to other cells, like this one. But for example, this 1, 2, 3, 4 cannot connect to this cell down here. And that is, you have to consider this if you are like putting your problem on this machine. Putting your problem on a quantum computer in general means, and this is very different to many other computing tasks that we are doing today, is the most important and the first step is you must rewrite your problem into a QUBO, a quadratic, unconstrained binary optimization problem, like with this formula. At the end, whatever you want to solve on a quantum computer, you must bring it in this formula. Discover the weights and the strengths for the coupling, and if you can do that, then you are done. And then it's very easy to put it on a quantum computer. There are algorithms which then maps this. Actually, this, if you have a clue of mathematics, this can be represented by a matrix, of course. But then you have to map it on the hardware topology, dealing with all the couplings between the different cells. The downside of this is that this reduces the probable problem size. As I said, the quantum computer has like maybe 2,000 qubits, but some of the qubits are needed for communication with other cells. And they are lost for the pure problem size. It's a huge disadvantage in the systems today, because the problems that you can put on the quantum computer are really, really small. And this is not only compared to high-performance computing field, or to huge applications in data science. This is really small, in any sense. Like, imagine a problem of your domain where you can store information with about 1,000 bits. It's not very much. Well then, actually, moving on in programming quantum computer, well, bringing this problem on a quantum computer means you copy the weights and the coupling strengths to the actual quantum computing chip, to the physical qubits. That's easy, that's some engineering stuff. And then the magic happens, or like the quantum physics stuff happens, which I cannot really explain. That means solving the problem. And solving the problem means you do an adiabatic change of energy levels. This is triggered by some event, and then the energy levels on the system changes. And you have a start energy system, energy distribution, and you have a target energy distribution. The target energy distribution defines the solution of your problem, but with a certain probability only. It's not if you're doing this process once, you get a solution, but you cannot sure if this is really your solution of your problem. You have to repeat this process like tens of thousands of times. So 10,000 times repetition is a typical number that we found out on the quantum computer. A good thing on a quantum computer is that it really finds a global minimum. So for example, so we are doing an optimization problem, a graph, and typical algorithms often find only like local minima, like this or this one, right? If you have done work with optimization problems, you often find this local minima. But a quantum computer always finds the global minima in your domain space, in every dimension, not only in 2D, but also in higher dimensions. That's really advantage of this system. Yeah? But the problem is, as I said, you must bring your system on the topology of the hardware, and if you can do that, it finds the global minimum, the global optimum of your problem immediately. Not like computing for days or weeks or months or years, as in many other problems. That's really an advantage and a hope that we have in this system, that it can solve this kind of problems with global minima immediately. So the software development is like in any other, for any other hardware. You have some kind of API for different languages and supporting tools and so on. And programming with Python is very easy. There's an API by the company D-Wave, which you can just import a couple little stuff, connect to the quantum computer with your credentials, get some information about the hardware, and this is really important because when they have these quantum computing chips, not every qubit is usable because of manufacturing errors. And if you want to use the quantum chip, you have to get the information which qubit is available actually for your computation. But that's a little of work. And then you can run the solver. It's just a Python call, stored icing. The process is called, the probabilistic solving process is called icing. It solves the problem, in this case, for 1,000 times. And then you can read the solutions, minimize energy, see target, and yeah, then you get solutions. And as I said, the problem in this kind of computing is you get many solutions. For example, this is, I don't know how many runs, very few runs, but for a small problem, you have one solution which might be your real solution of your problem because it happens more often than the other solutions, but you have other solutions which also occur. when you run this, maybe in this case, I don't know, 20 times or so. And the distribution can look very different. Sometimes you have a huge peak for one solution, and then it's most likely that this is the solution of your problem, especially for problems which reflect problems of the real physical world. Because we also then have two physical systems, and physics makes sure that there is some solution. That's a nice thing, actually. If you try to trick out the machine or to cheat on the machine, and you generate a problem with random numbers, then you have an equal distribution of all solutions. Yeah? It shows you that you like to cheat on the machine. It's very nice. Yeah, the time is almost over. What? Oh, I'm finished anyway. So I started earlier, that's the problem. Yeah. Okay, summary. So my only hope is, and indications for that Python is or will become the standard programming tool for these kind of technologies which are presented. High performance things, data science, and of course in the future quantum computer and any other technology which might become up. So that will be a good thing, I think, that we all can do programming this stuff in Python. And that's the end of my talk. Thank you. If you have questions, maybe you can ask now. We have 4 minutes, or you can get a coffee with me outside, because I now need a coffee. Thank you.
Thank you very much. So any questions? Can you go that side?
I'm probably going to do it like that. Inside you mentioned that these quantum computers are going to find a global optimum. Has that been shown theoretically that it's always going to find it? Or was it rather purely empirical?
Yes, it was shown in science. Oh, yes. Oh, so the question was, I was shown that the quantum computer finds a global optimum. And if this is shown theoretically, and yes, there are scientific papers, which I didn't read, which tries to prove that for this kind of technology, how in the way it's realized here at the D-Wave systems. Yeah? Yeah, there are a lot of paper with physicists. There's another question.
Same question as before. When you have, as I understand, an optimization problem, you have, for example, the gradient descent algorithm. So you do random initialization of the model and run this algorithm to multiple times comparing results. Now, is it a different algorithm that you use in the quantum computer, or is it that it can do a lot more simulations to compare more results quickly?
So the problem is there is no algorithm. So there is no algorithm. You said you're asking if you are using a similar algorithm on a quantum computer. But no, that's a different assumption, the wrong assumption. We have no algorithms on a quantum computer. It's just a physical effect that takes place. And the physics generates a solution, but there's no algorithm. It's very, very different to solving optimization problems on classical computers. You just provide the formula, the optimization problem, and then the physical system generates the computing, the solution, and I don't know how it's been done. And also, well, I think the people at the company who built this computer don't know how it's been solved. Yeah? That's my impression. And when we are working on collaborating with them, they pleased us not to send physicists to them. People from software development, or at least mathematicians, would be okay, but physicists always ask the wrong questions.
What is your opinion on Julia?
So, and what?
Your opinion on Julia?
Julia. Oh, yes, yes. Haven't used it in practice, but I think it's very promising for HPC applications in data science. And I know that my observation is that more and more people are using it. And it's one of the competitors of in Python in this field, together with Go and other languages. Yes.
Yeah, one practical question. You said you have to repeat the thing about 10,000 times. Does it mean you have to wait a second between each 10,000 of these, each calculation is 10,000?
Yes.
So it takes 10,000 seconds for one run.
Yeah, yeah. In general, this is true. In detail, it's more complicated, actually. You can combine this kind of stuff, and the time, the 1 second waiting time, depends only on also on the energy level for your problems. So it's more complicated in detail. And you can write 10 papers for every problem that you are solving on the quantum computer. And that's a good thing if you have to, as we as a scientist, because we have to write papers as our daily work, and it's a good thing.
I have a question on the distributed computing part of the talk. Do you have to plan ahead which hardware runs which operation in the pipeline that you shown before?
Which hardware and which hardware is using in the...
Yes, I assume that you have different machines, distributed machines.
Yes.
And you build a pipeline so that each machine runs a particular computation.
So in
My
general,
question is, you have to plan ahead which machine runs which kind of computation.
Yeah. Yeah, and this is, in general, you have heterogeneous machines, and this is really the task of the scheduler. The typical examples that are shown have more or less good scheduling algorithms with doing this task. Yeah? But this is not really related to the Python side. The scheduling and planning ahead is a problem. As I said, NASA is doing that with the quantum computer, and this is really one of the problems that you have to solve if you want to have a good overall performance, yes. But it's important, yes.
We're on time.
Okay.
Thank you very much again.
Thanks.